And those are going to be led by our sub-team leads. So electromagnetic induction by Tyson Morley, X-ray fluorescence with Edmund Muniz, ground penetrating radar, Olga Vargas, mid-infrared spectroscopy with Andrea Williams. And then Chad will go over kind of a wrap up and kind of the next steps for where our team is going. And then if there's any additional time at the end, we'll take some more questions and answers. All right, so starting off with the who's who, Chad and I are co-chairing this focus team, and I think I can speak for both of us in saying that that is not because either one of us is necessarily an expert in any of these technologies, but we are here and excited to facilitate everything that's going on, and I know I'm excited to learn more about all of these different technologies that I've heard about, but haven't necessarily used myself. So yeah, that I just went over that I'll be presenting. So we have the mid-infrared spectroscopy. That's Andrea Williams. She's a soil scientist out of Duluth, Minnesota. Ground penetrating radar with Olga Vargas. She is our soil scientist in Greenwich, New York. Electromagnetic induction, Tyson Morley. He is an MLRA soil survey project leader in Altus, Oklahoma. And X-ray fluorescence with Edmund Muniz, the state soil scientist in New Jersey. So what is our focus? We are a, kind of newly established focus team. So basically, we want to help move soil science forward by bridging the gap between our historical tools. Think of our shovels, our augers, sharpshooters that we've used and love so much, but kind of incorporating field technologies as well as other technologies that can enhance soil survey as well as technical soil services. Like Jen said, this spans both soil survey production as well as the services we provide on the O1 side. And all of that happening through voluntary participation. Chad and I want to emphasize that, we need everyone's participation to make this focus team a success, but we don't want people, begrudgingly being told, oh, you have to participate in this. We really want and hope that people will voluntarily participate. And I think it's also worth noting, like, technology is a huge term, right? There's so many different things under the umbrella of technology, and the technologies that we're presenting here today, those aren't the only ones that we're going to focus on. We are open to many different kinds of technologies, and there's definitely going to be overlap with other focus teams, such as the digital soil mapping team and others. And then, possibly even the training team as we start to identify training needs. So our charges as a focus team are to identify both internal and external audiences. The focus teams are not specific just to NRCS, but include all of our partners in the National Soil Survey Cooperative. So we look forward to participation from all. We want to promote an environment where any employee or cooperator can learn and discuss about any of these non-traditional or they're not new, but basically these field technologies that we have at our fingertips and how those can aid in NCSS activities. We want to maintain an active inventory of equipment so we know who has what, who's using it actively, who may need some help, and then update and encourage training opportunities. And I want to kind of note that our sub-team leads are sub-team leads within this focus team, but that does not necessarily mean that they are now the national leads for these different technologies. They have very graciously volunteered their time because of their use and experience with some of these different technologies to share that with those who are interested. So again, our technology focus team is only going to be a success if we have you all as participants. So we need you. Join in the conversation on our Microsoft Teams team, and I will drop this after I'm finished into the chat so you have that direct link, or you can email myself or Chad and we will be happy to add you to the team. Once you're in the team, or at any time, you can contact any of the members to provide your feedback, your questions, share your experiences. And this is the kind of just an introductory who we are and what we're doing and where we're going webinar. But this will be the first of many. We'll start kind of, some of the sub teams may have focus sessions, open sessions where they're working actively through different issues, questions, helping people utilize these technologies. And it also, we have so many new, it doesn't matter if you're new or in the middle of your career, at the end of your career, this really can give you the opportunity to be a local leader in using these technologies in your field area. So hopefully, maybe you have something that's been sitting on your shelf, you're like, I wonder what that actually does. And, maybe this is an opportunity to dust it off and get the help you need to get it up and running. So with that, I am going to pass it over to Tyson. I see you're on, to tell us a little bit about electromagnetic induction.
I am on. Share my screen. Can you see that correctly, or is it the wrong one?
It looks great and it has the right name on it.
All right.
That's your
hello.
That's your presenter window.
I do this every time. That's the one.
That's the one.
There we go. Okay. Hello. My name is Tyson Morley. I am the sub-team lead for the EMI, sub-team lead, we'll call it, the electromagnetic induction. Again, I am the MIR leader in Altus, Oklahoma. Also supervise the Abilene, Texas office as well. There's my contact information. If you have an EMI, we're going to talk about this more later. But if you have an EMI and you have not been contacted by me in the last 2 months, please email me what you have, what model it is, and what status is it in, because I'm trying to update our database. I currently am operating a Genonics EM38 MK2. We'll show a picture of that here in just a second. What are we talking about? EMI, electromagnetic. This is the best definition I could find. Electromagnetic induction sensors measure changes in the apparent electronic conductivity in the subsurface without direct contact with the sample volume. I'm not going to read all that. You all can read it just as well as anybody. But I want to include down here that the apparent electrical conductivity will increase with soluble salts, water, clay content, and temperature. This is extremely important because these are the variables that you need to take into consideration when you operate an EMI. EM machines are typically used in a heavier soils, not your sandy soils. That is a huge distinction between it and the ground penetrating radar. But water content, if it's extremely dry when you run this machine, it's going to pick up on any areas that have a higher salt content or higher clay content. If you have it when it's extremely wet, you'll also pick up on those changes, more so on the soluble salts. But when it's in between, when you got going from a very wet period to a dry period, I'm out in the plains, we're mostly dry in this particular area. But when you're going in those transition periods, if there's a moisture difference between your concave and your convex parts of that field, you're going to pick up on moisture differences and not so much salt or clay content. It's kind of a tricky deal to work with. There's 3 main EMI sensors out there. The Dualum is, I've seen this one in the field, a Dualum 1, and there's a Dualum 2. They are typically a little bit longer and can penetrate deeper in the ground. There's a picture of the EMI or the EM38 MK2. That 2 is what I operate, the orange one there in the middle from Genonics. And then the Profiler, I have never seen one of these in the field. I know they exist out there and I would love to see them one day. I also want to draw attention to the pictures as well. There is all different types of operations in sleds that are being made. The biggest issue is this being electronic or a magnetic issue. You can't have any metal. That's why they're being pulled by a rope usually about 8 to 10 feet behind a UTV or a pickup, or you can walk them. But if you walk them, you can't have boots with metal shanks in your boots. It's a big deal. Even operating these with a watch on can sometimes affect the readings. They're pretty sensitive. The advantages of the EMI: they're non-invasive, meaning we're not digging up the whole field. The speed of operations: you can drag as much as you want to in one day, if several hundred acres if you needed to in one day. They're moderate to high resolution of subsurface features, larger volumes of data collected. They provide more comprehensive spatial coverage of a specific site, and there's a greater confidence in the site assessments. I will also say that you cannot operate these without pulling soil samples for testing across the field. You have to field verify the readings that you're getting. The limitations: results and interpretations are based on recognized and spatial patterns within the data set. Methods are not equally suited for use as all soils. As I mentioned, sandy soils are not a good use for EMI. Does not include the need for direct observations. That's what I was saying. You still need to pull samples to verify the readings that you're getting with your EMI machine. I would be amiss if I didn't mention these two gentlemen, Mr. James Doolittle and Wes Tuttle, were the pioneers of this technology. I had the distinction of working with Mr. Doolittle. John Warner invited me up for Mr. Doolittle's last field visit, and I was the last one he trained before he retired. So I don't consider myself an expert yet, because I don't know if I'll ever be able to get to his level. But I would be remiss without mentioning those two today. What now? According to the database I have, there's 49 EMI units within the NRCS. That database needs to be updated, and that's where I need your help today. Where are they located? Are they operational? And if not, what do we need to do to get them fixed? Surveys. Was it sent out? I sent one out a couple months ago, and there was to the 24 users that I had in my database. I got 7 responses. I appreciate all 7 responses, but if you have one of those EMIs, I would love to get that number up. 100% of the people that responded to that survey are interested in some kind of training in the future on the EMI and how to use them, how to use the data, how to process the data after the surveys are completed. 100% of the responses are actually using the EMI for TSS in their day-to-day use or over the years. There is some applications that can be used in a soil survey. One particular is if you have a saline sodic map unit that you're looking at, maybe the composition, and you may be able to map out the hotter zones that maybe you're if you have a 2-series con association or something like that. Bi-monthly. One thing we're looking at is either a bi-monthly or quarterly teleconference. I'd like to discuss the use of the TSS and how they can be used in soil surveying. I'd like to discuss the maybe tricks and tips for operating these units. And then also I'd like to discuss how to incorporate this technology into DSP/soil health initiative. And that's actually what I'm focused on in this year and next year, is how do we incorporate this technology to give some better information to be useful to the landowners and to the survey as a whole. So with that, I told you I'd be quick.
Tyson, thank you so much. We have several questions in the chat that I'm going to address quickly. We may not be able to take all of them. Diane Lamb asked if you had addressed the USDA GSU Geological Services Unit on what they might have. So that may be a route. Dave Harper, Dave Harper says they have 2 units in Virginia, State Soil Scientist of Virginia, and he wondered how that technology has changed from the late 1990s.
I actually have 2 units myself as well. I have an old EM38 that is analog, and it doesn't have GPS capabilities or anything. The EM38 MK2, the newer unit I have, is has an Archer 2 data logger that's GPS, and it's wireless. It's Bluetooth to the unit, so you can hold it either walking it or if you're pulling it with an ATV, and it allows it to collect a extremely larger amount of data. The old analog data one, it can be converted to the new one. So if you want to go do that route, if it's a Genonics, you can contact them and they have a kit to update it to the newest, latest, greatest version. And there's software that goes along with it. Does that answer that question? I hope.
Thank you, Tyson. Unfortunately, that's all the time we have for those questions. Dave Gehring, we will get to yours after the session, Dave, if that's okay. We have to move on. We have to get to the top of the hour at 3. So thank you so much. Amy, would you like to introduce the next person?
Sure. Edwin is up next with X-ray fluorescence.
Thank you very much. Hello, everybody. I'm Edwin Muñiz. I'm the state soil scientist for the state of New Jersey, and then I'll be talking about PXRF or portable X-ray fluorescence, and how we can use it for soil survey, even for soil classification is possible to use. I'm not going to be talking too much about the part that I do the most, which is technical services, but that's something that we can talk later. If you have any questions on that. So some of the application of this equipment is to measure everything at the elemental level. So it doesn't measure compounds. The focus that I use this equipment is for lead and arsenic. But we can look at many other elements, and I will show that in a second. So the way that this works in the elemental level is that there is using X-ray energy to measure amounts, concentrations of different elements. And it can be assisting in the description, calcium content, soil weathering, soil mineralogy to a certain extent, lithology, for example, serpentinite. Serpentinite is characteristic to have a ratio of nickel and chromium, so you can use that looking at those elements, and then you can see the differences between soils that are serpentinitic and soil non-serpentinitic. Also, carrying exchange capacity, there's some papers written about that. There is many papers using this technology by Dr. Weindorf. I think that he's now in Louisiana. He's done a lot of research doing this. And also for soil horizons. You can see in this picture, we have, let me look at the pointer. So we have the equipment that we have is a portable X-ray fluorescence. There is many brands, many models. This is the one that I use. And you can see here, we have it connected by Bluetooth to a data collector. Even though that the equipment save all the data inside or in itself, I have connected to the data collector, and that data collector I have it connected also to the high resolution GPS unit. And the reason is because when I'm doing this, I'm doing a high density data collection in small areas, and I really need the resolution between points, and also when I'm close to buildings and that kind of thing. So this setup works very well, and it provides excellent data that I can just put directly into GIS for any kind of a spatial analysis. So how this work? The way that this works is the energy, X-ray energy. What it does is it excites some of the electrons in lower orbits, and those electrons they shoot out of the orbits, resulting on electrons from upper orbit moving to the lower orbit. So as you can see here, that movement generates energy. That energy is fluorescence, and every element generates their own energy, or is characteristic with a wavelength, if you will, of that energy. So the equipment pick up that fluorescence and the amount of it, and then they can produce an output. In this case, it could be part per millions or percent, depending on the concentrations, and depending also in the equipment. So as I mentioned before, this is all the elements that the machine can pick up depending on the calibration and the model. So you can see it looks for a lot. So the potential on using this is incredible. And the reason that we use this model is because these limit of detections are within the ranges for the cleanup standards for the state of New Jersey. So that means that, you know, when we're looking, basically what I said for lead, we're looking the cleanup standard for lead in New Jersey is 400 ppms. So you can see the limit of detection is 2 to 4. So, you know, way lower than, you know, what I need is a lot more than that. So so these ranges work very well for either for arsenic and lead. So you can see that, you know, this is one of the things that you have to keep in mind, the limited detections of the equipment, depending on the kind of studies that you want to do. So make sure that equipment can read the concentrations. For example, here there is mercury. In reality, I don't have too much confidence in this equipment for mercury. Mercury is one of those elements that there usually are in low concentration, and most of the time they're measuring ppbs, which is part per billions. So you can see that the detection limit is 2 to 4 part per million. So it's not very reliable for mercury. So this is an example. That's something that you have to keep in mind when you're using this equipment, and for the reason you're using this equipment. Like any technologies, there is limitations. So some of the characteristic of this instrument is it's portable. As you can see, you know, there was like one of those speed guns that the police use that are small. You can collect a lot of point data. That's the, you know, in one day you can collect hundreds of point data. The data collection, we have it set it up for 1 minute. This varies by equipment. My predecessor, Dr. Richard Shaw, he did some studies on looking at the different time data collection, and 1 minute was a good number to get good reliable information or data. The collection could be up to 26 elements in one reading. So you have a lot of information there. The point data and the spectrum for the data, you can download it as a CSV. So you can put it in Excel, you can put it in GIS, you can put it in any software that reads a CSV for analysis or to show the data. And a special software is necessary, so that's, you know, helps us a lot with you know, loading software in government computers that, you know, it's difficult, it's a long process, and since there are not that many of the equipments available, you know, sometimes it's the time that the IT will have or OCI has to spend certifying the software is not really worth it. So so I think that's one of the decisions that help in the selection of this equipment. As I mentioned, the collector or the equipment is connected to the GPS unit. There is recommended using a calibration every 20 readings, but the calibration takes about a minute. So that's nothing. Also, is a huge limitation. And then the good thing about this is that this PXRF you can use in combination with the MIR and also EMI data collection. So you can complement this equipment with other ones and vice versa. So some of the limitations, if you have moisture content greater than 20%, we could reduce the reading accuracy. So you have to be aware of that, the percent of moisture in the sample. You can always take a sample to the office and dry it and then make a correction, but just keep that in mind. A sample has to be uniform. So if you have a big sample or bulk sample that you send to the lab, you might get a huge difference between your reading because the capture area for the instrument is very small. So one of the best practices for bulk samples is taking several readings and then present results as average readings. So those probably will be a lot closer than the bulk sample data that comes from the lab. Or the data comes from the lab from bulk samples. There is some interference or some overlaps with other elements. This is, there's some elements that are the fluorescence is close. Some of them, for example, will be lead and arsenic. So if you do a right calibration with equipment, that limitation can overcome. But if you don't do a good calibration with the equipment, you can have a poor precision. So something also that have to be keep in mind. And as I mentioned before, the instrument has a small detection area. So you have to keep looking at your data when collection, because if you find an outlier, you should retake another reading because maybe your sample is being taken for a small chip of, for example, a paint chip that is in the soil, and then your readings are not going to be accurate. So some of the things, like for taxonomy, since there is a lot of people from the soil science division, this is something that I will use a lot. This is an example of a soil here in New Jersey, Nixon soil. And you can see that has an argillic horizon. The soil is forming all alluvium from derived from red shale over some coastal plain material. And there is a difference in potting material in here that you can see here. So why I'm showing this? So what I did was I went, this is from the soil pit at Rutgers University in New Jersey. So we had the soil phase and we created a grid, like you can see here is a 10 centimeter grid. And I took readings in each one of the grids. So, and then I plot those readings over the area photo, over the profile photo, and then look at the different concentrations, and we can see the calcium. It was high because this is you can see there is a plow layer here, or AP horizon, and the concentrations of calciums are then get reduced. So there was something interesting. So you can pick up that. Other thing that I did was looking at the lead in the soil. So then you can see there's a big concentration of lead, and then it got reduced with increasing depth. And the reason is that there is a lead deposition by atmospheric deposition in this soil. And if I forgot to put the area photo, but if you will look at the area photo, this soil is located, or this plot is located close to a big highway. So there is a lot of lead that has been deposited by atmospheric deposition in this area. There's something interesting that we can see with all these readings. And also with the total concentration for iron. And then we can see that the concentration in iron also correlate with argillic horizons. So there is also some papers written that there is some correlation of in some soils with clay content or argillic horizons and iron. So we can see that expressed here very, very well. So it's another way that we can use it. And lastly, also I look at the total titanium, because I've seen other papers also that mention that there with the reduction of titanium is an indicator of weathering. And we can see also that it could be a difference in pattern material. And we know that there is a difference in pattern material between this upper part and this lower part. And we can see an increasing in titanium in this horizon. So there's kind of things that are interesting, and there are a very big application of this technology in the soil classification and other activities within the plant science division. So this is the end of my presentation. I'll be happy to have you a part of the subcommittee, and we can learn more together about this technology and applications with the soil survey, and then I can provide you all my experience using this in technical soil services. Thank you very much.
Edwin, thank you so much. We had a couple of questions in the chat that were answered by Dylan Bodette and Christine Ryan. So I don't think we'll need to expand on those too much more than what they already have by answering those questions. The first one was, in case you wanted to expand, Edwin, can the instruments read all elements in one time reading, or do you have to conduct different elements separately to get the data? And Dylan answered, total elemental it measures total elemental concentrations.
Yeah, but and Dylan has a lot of experience on this. Probably, yeah. You know, he's been using this longer than me, and he's right. Yeah, the instrument, when in 1 minute give you the output for 26 elements in one shot.
Thank you, Edwin. I really appreciate it. I'm getting bad network quality, so if we have some bumps, just bear with me.
That's all right.
Thank you so much, Edwin. Next, we have Olga Vargas with ground penetrating radar. Olga is out of Greenwich, New York. She's a soil scientist. Olga, if you are ready, you can take the wheel.
Yes.
Or did I do everyone out of order?
No, I think you're good. Can you see my screen?
Thanks. Yes, it looks good.
So now, my name's Olga Vargas, and I'm going to be covering ground penetrating radar. As we mentioned earlier, Jim Doolittle was our main and West Tuttle, our ground penetrating radar national leaders, and they have since retired. And we've had this technology for, I think, almost 40 years now. In New York, we've had it for over 20. We started out with grayscale images and thermal plotters, as you can see in this picture, and then we thankfully transitioned into the color age and digital technology. We used to have to pull the radar on a wagon too. So now we have carts to help push them too, or we backpack them a lot. So we've had a lot of retirements, and while this technology is not new, you know, there may be units out there who aren't being used. So hopefully I'm here to encourage the future radar rangers to pick up the equipment and learn how to use it. So I'm going to talk about how this equipment works. And the way the GPR works is that there is a control unit and an antenna that you drag along the surface, and that control unit is emitting a wideband frequency. And as that wideband frequency travels through the ground below it, it is traveling at a certain travel time that is dependent on its dielectric properties. And so if there is a contrasting strata below, like bedrock, that has a different dielectric property, that travel time will change. And then that pulse is either reflected or absorbed, and the rate of travel changes. And that change will let us know, in travel time, can be converted to a depth scale if we're properly calibrated. So we will not only know if there's a contrasting strata like bedrock, but also at what depth it is if we're properly calibrated. So our antennas, we have a wide variety of antennas throughout our agency. Those that are below 200 megahertz are actually regulated by FCC, and the ones we have are grandfathered in. So if there's an antenna in your state, you want to make sure you take good care of them and keep them going. And but our go-to antennas are usually the 200 megahertz and the 400 megahertz. Now, while technically the 400 megahertz says it goes to 3 to 4 meters, that's probably mostly true if you're really dry, sandy soil. Here in the Northeast, with the moisture that we have and the loamy tills that we have, we usually get about a 2-meter depth out of our 400 megahertz antennas, which work really well for our soil survey work. And then when we have soil survey work that requires a little deeper resolution, we will switch to our 200 megahertz antennas. Or if we're working on frozen soils, we tend to switch to the 200 megahertz antenna then too. In recent years, as we have more of a focus on soil health and looking for that better resolution, we've the 900 megahertz antenna has become pretty popular, because the higher the frequency that you have in your antenna, the better near surface resolution you get, but you're only going to be able to see the first 2 feet. But it really helps us pick up those compacted layers, or really the high resolution near the surface that you might not get with the lower frequency antennas. But like I said, we have a whole bunch of different antennas throughout the country. So depending on what the survey is specifically used for, and I try to bring at least 2 antennas because the site conditions may affect its ability to go through the ground surface. So how we are applying these for soil survey, my favorite are depth to bedrock surveys, because as you can see from this diagram, they show up so nicely. You can really pick up that restrictive layer. You know, we can play with grayscales, color scales. We can change the ranges of our scales to really only pick up those really contrasting strata, as you can see in this diagram. And then we can see the thickness of them. In sandy soils, we can pick up water tables. We can pick up disturbed soil, so they're really good for urban soil surveys. We're actually going to be running geophysical surveys for our urban dynamic soil properties. A lot of states have used the GPR for their subaqueous soil surveys. We've put them in little floaties, to either that or waited till things are frozen over. And then we've also used them for ecological site descriptions. Down in New York City, we have these tiny little grassland areas that are on serpentine bedrock. So we've used them on those sites for ecologic descriptions. And then when it comes to the conservation side of things, you know, we've used the GPR for detecting sinkholes. You know, sometimes after we found them, we look to see if there are other areas of potential weaknesses. We've used them for manure storages. Sometimes we get called in after things have gone wrong. It's always nice to go to a site before things, before you find how shallow that bedrock is. But you know, we take it as it comes. We've also looked at dam seepage and lake sedimentation studies on the conservation side. And then when it comes to TSS and our urban ag areas, we've worked really well with our Parks Department, the National Park Service, you know, our partners on soil survey, where we're able to offer technical soil services while they support us on our soil survey activities. And it's provided a really nice collaboration projects, and it really helps our soil surveys to be able to provide that technical soil services. And then we've also held geophysical ag workshops, which I really like. And we held these with some of our universities, but also with our CUNY students down in New York City, which is really nice to be able to give them a day at the extension farm further out in Long Island, and not just expose them to ag, but also expose them to geophysics and ag. And those have worked out really well. And then as far as site suitability, where does the radar work best? We do have a web soil survey interpretation that Doolittle developed before his retirement. That is a site suitability map for the U.S. Those sandy sites tend to pop up on this map, and those coastal sites on the East Coast and the West. And those are areas that are the most suitable. Not to say that I haven't used the radar in sometimes heavier soils, but then you really need to pay attention to moisture and the weather of the week to make sure you have the most optimal conditions. And then interpretations, you know, there are ways we can process our data. I really like to, but also I really like to use the EMI and the GPR together a lot. We are very low tills, so we're fortunate we can use them together. And the EMI is a great reconnaissance tool where it can help me target and limit the scope of my GPR work, because the EMI can cover so much area and the data is faster and quicker to process. And then I can try and correlate some of those EMI values to the values of the profile values that I'm getting from the radar. GPR, there's only one company in the US that manufactures our units. So all our units are manufactured by GSSI in New Hampshire. And they also provide the software and the training that we use to process our software. But we're always here to support each other if you're needing assistance in processing the data, you know, trying to reduce some of the noise. Wideband, because it is emitting wideband frequency, sometimes noise from if there's an airport nearby or power line or engine noise can cause issues. Other wideband frequency tends to interfere with our equipment more than our equipment interfering with them. We turn off our cell phones when we're using our equipment, which is sometimes really nice as well. So there are things to consider when running a survey. And then I can't bring up calibration and ground truthing enough. You know, there are a few times where we're not allowed to excavate at a site, which is why we're switching over to geophysical tools. But whenever possible, we try to ground truth as much as we can. When we calibrate, we're burying a known target to a certain depth, and that allows us to estimate the travel time and calibrate to that depth. And I used to use like a 10-inch cast iron lid for my calibrations until it finally broke into little pieces. And lately I switched over to like a 10-pound weight that's nice and heavy. And so it's still a pretty good target. And then if you have questions, you know, our future webinars, we can try and troubleshoot any issues people have had or ideas for, that's it, that they may have. So just let me know.
Thank you so much, Olga. We have one question and we're kind of getting close on time. If we can get this one really quickly. If GPR is used in subaqueous soil investigations, how does the depth of the water affect the effectiveness and the depth capacity of the unit? Does the radar penetrate water more or less effectively than soil or geologic materials?
Okay. In the subaqueous ones, they've either done them in the winter where they're dragging it over ice and you do have to use the lower frequency antennas, or we put them in when it's not frozen, we put them in plastic floats and little dinghies because you can't have metal around it. And then like the operator is in the adjacent boat, and we've done transects that way. So it can be done over water. You're switching your antenna to get more effective depth scale.
Thank you so much, Olga. And next we have Andrea Williams, a soil scientist out of the Duluth, Minnesota office. Thank you so much for presenting today, Andrea. And we can see your slide. It looks great.
Okay, great. Thank you. Hi, everyone. My name is Andrea Williams. I'm an MLRA soil scientist in Duluth, Minnesota, and the MIR sub-team leader. This presentation today will give you an introduction into how mid-infrared spectrometry, which I will refer to as just MIR, how that can be used to analyze soils, and how the Soil and Plant Science Division is implementing MIR for soil resource assessment. There we go. Thank you. All right. By definition, electromagnetic radiation in the mid-infrared or MIR region of the electromagnetic spectrum has wavelengths between 2,500 to 25,000 nanometers. And the study of interaction between matter and radiation is known as spectroscopy, or in the case of interaction between soil and MIR radiation is MIR soil spectroscopy. However, spectrometry refers to using that interaction to make measurements of material properties such as soil carbon or clay content, and that root meaning of the suffix metry refers to measuring something. Because different soil properties absorb MIR radiation in different regions of the MIR spectrum, statistical methods can be used to calibrate those absorption features to known conventionally measured soil properties such as carbon and clay. And once that calibration has been prepared to estimate a soil property from an MIR spectrum, that calibration can be used to estimate that same property for an unknown sample from its MIR spectrum. And while not all soil properties lend themselves to being calibrated to MIR spectra, many of them do, including ones that are important in soil taxonomy and soil health assessment. A few examples of soil properties that lend themselves to successfully being calibrated include cation exchange capacity, organic carbon, clay content, 15 bar water, pH, calcium carbonate equivalent, to name a few. There's two models of MIR spectrometers currently being used by NRCS. One is referred to the production instrument, and that is used for collecting large numbers of MIR spectra, such as used at the Kellogg Soil Survey Laboratory. And another is referred to as a single sample instrument used by the field offices not needing the throughput capacity of the national laboratory. And please note that no USDA endorsement is implied or should be inferred when referring to particular brands or models of these instruments. And that Bruker Vertex 70, shown in the upper panel, is used at KSSL to build our national library of MIR spectra, which the local NRCS field offices use to build calibrations for estimating properties in soils in their local areas. The Vertex 70 has a high throughput accessory that allows it to scan many samples per day. Once calibrations or the models that are built using the Opus software with Quant2 package, unknown soil samples collected in the target area can be MIR scanned at the field office using that single sample Bruker Alpha spectrometer shown in the lower panel. That alpha spectra are then processed through the aforementioned calibrations to rapidly estimate soil properties. The alpha spectrometer collects spectra of one soil sample at a time and takes approximately 20 minutes to scan 4 replicates of the sample. The instrument may be used to analyze a penon or 2 per week in the field office, as there's also time that's needed to crush, sieve, dry, and mill the soil samples into a fine grind. And building a national spectral library is feasible because of the National Soil Archive housed at the Kellogg Soil Survey Laboratory. The archive represents decades of natural resource inventory, and these archive samples were already analyzed by conventional methods of analysis for key properties such as carbon, clay, and CEC. So then scanning those same samples for their MIR spectra allows building calibrations at local or regional scale. I can't emphasize how great of a resource this is for us. And this map illustrates the current coverage represented by the KSSL MIR Spectral Library in the United States. As the MIR library expands to underrepresented areas, more soil sample variability can be captured in the calibrations, making MIR more broadly applicable with increased accuracy. NRCS first piloted this technology in Salina, Kansas, and the results were published in a SSA journal paper in October 2019, and I will share that DOI for the paper in the chat now. It's also noted in this slide, as I know this is being recorded. The very attractive correlations and errors demonstrated the viability of using MIR spectra to estimate soil properties for purposes such as soil classification, survey, soil health assessment, and monitoring. The results of the pilot project have resulted in increasing investment by NRCS in MIR technology. In terms of overall objectives, the NRCS Soil and Plant Science Division supports useful innovation in soil analysis, and MIR soil analysis is a prime example of this. It is a versatile tool for soil assessment, and compared with conventional methods of analysis, MIR offers field offices fast, safe, with no chemicals needed, and reliable estimates of key soil properties by using legacy samples and data. So the equipment that's needed for an MIR laboratory includes a low temperature oven that's used to air dry soil samples from the field before they're sieved, a mill that's used to grind the air dried sieved material, a spectrometer that's used to collect mid-infrared spectra on the soil samples. Additionally, general consumable lab supplies are also needed. And at the end of fiscal year 2021, MIR technology has been deployed to 15 offices, with another 6 planned this year in 2022. These locations include both Soil and Plant Science Division field offices and a few state NRCS offices. And the offices are in various stages of setup, training, and development. The invitation is open for other NRCS offices to request to participate in this promising program in predictive science. I would encourage you to speak with your MLRA office leader or regional director about your interest in purchasing that equipment. Participating NRCS offices designated one soil scientist who is available and interested to be fully trained on all aspects of the MIR, including querying for calibration data, building calibrations, and using MIR laboratory equipment. The training is a 5-day course, and for the first year, up to 25% of a full-time employee's time may be needed to build and validate calibrations. After that first year, the field office could plan on 10% of a full-time employee's time to lead and maintain the MIR field office laboratory. Approximate costs to onboard MIR technology are shown here. The first year expenses cover equipment and validation services, in which field offices send a percentage of their true test samples, which are samples collected from the field and not used in calibrations. They send those to KSSL for conventional analysis to compare the results with the estimates afforded by MIR. And seeing is definitely believing when it comes to the performance of emerging technologies, and validation of model performance with true test samples is a critical facet of the MIR quality assurance program. Currently, an online course is offered to offices receiving MIR equipment in 2022 and NCSS scientists. Full installation of equipment is needed before training is scheduled. And in closing, if you are interested in discussing this promising program in predictive analysis, please feel free to contact any one of those listed here. Additionally, if you are using MIR spectrometry in your office, please consider joining the focus team to share successes and challenges you may experience. This is a very exciting technology, and I cannot emphasize enough how valuable the data we have from KSSL with the decades of conventional analysis and our growing MIR Spectral Library. So this concludes my part of the presentation today, and I'll turn it back to you, Jen. Thank you.
Andrea, thank you so much for doing that. It was a wonderful presentation. Everyone did such a good job. I have enough time to ask one more question for Tyson, if you don't mind, that I could not get to earlier. And it was from Dave Gehring, the research soil scientist in Owensboro, Kentucky. What about Veris? Is anyone using Veris machines to measure EM that can cover much more ground than the machines listed, you know, for some of these machines? Does anyone know about that technology, if we have access to that?
The only time I've seen Veris machine used is in the private sector. It is used here in town through the private sector. They can cover a lot of ground. Essentially, it is an EM machine. I don't know about their sampling and cross-referencing the known samples with their Veris machine. So if anybody else has got better information out there, we'd like to know. I think they're very expensive too.
I was wondering that too, especially if the private sector has them, you know that they're probably pretty pricey. So thank you so much, Tyson. I appreciate your answer. I do have one quick item I'd like to address before we go. I do want to announce that Christine Ryan, the state soil scientist in South Carolina, is on detail to the Soil and Plant Science Division for proximal sensing and taking inventory of our tools. She's also developing a roadmap and an outline of resource concerns and needs with these tools. She's taking stock of everyone's comments, and she's been in contact, I think, with Amy. So we hope to hear from Christine soon, and thank you so much for your work on the detail. In closing, I want to thank Chad and Amy for working with me today and the entire team of instructors today. It's been a really, really good day. And I think we've skirted a lot of the gremlins that we had this morning in our Adobe Connect session for our training. So thank you so much to everyone. Chad, did you have something before we left?
I want to say just a quick couple words. I know we're right at the top of the hour. I just want to reemphasize the fact that, you know, the focus team is a place where we want to promote these technologies and other technologies that other people might be aware of or want to discuss. Probably most importantly, we're not creating work for anyone. I know that some of these other focus teams, once you get put on them, you wind up getting additional workloads, and that's not what we're doing here. You know, we're not going to ask you to go into NASAS or develop training material. This is a place to network. Moving forward, we're going to have each of these technologies will be kind of their own sub-teams within the teams channel. They do plan on holding semi-regularly scheduled webinars. But again, you know, these people who you heard from today, they might be called the leads, but they're really just more facilitators or moderators. It's up to the participants to drive the dialogue of these teams. And I would say that participation in these teams will serve as a litmus test to see if any more resources need to be allocated towards the technologies. And what I mean by that is currently we only have one formal training for one of these technologies, and that's the MIR. You know, leadership thought that these tools were underutilized and needed a voice, and this focus team is a place for them to have a voice. And we think it's especially important for early career employees to get exposure so that this is not something you're learning about when you're 10, 15 years in, as I was. In closing, we hope the technology team will serve as a resource for you, so please use it. Please join the team. And with that, I will end the meeting.
Well, thank you so much, Tad. That's a great point. We really appreciate it. And thanks everyone for joining us today. We really appreciate everyone's time, and have a great day.